So I think we are ready to start the second part of our course. And to be honest, I think we will hear one of the most prominent persons on wireless power transfer in the world, which is Professor Naoki Shinohara. He's been working in this topic for a lot of years. Is also part of the MTT Adcom on IEEE and is responsible for the Wireless Power Transfer Conference this year and for several groups on wireless power transfer. So Naoki, you want to start? Thank you very much.
Thank you so much. Yes, sir. Yes, thank you. Thank you. No, I'm Shinohara from Kyoto University. Honored to be here to give a lecture for young scientists. And please don't forget, I'm the former chair of the Commission D, URSI. Yeah. So today I'd like to introduce a receiver technology. We call it a Rectenna, rectifying antenna. I focus on the rectifier technology mainly in my talk. So because Professor Nuno Carvalho explained overview of the wireless power transfer, and he covered transfer technology, beaming technology, and receiver technology in the morning. And in the afternoon, I focus on the receiver mainly, not only in this talk. And this is today's content. I have only 2 hours, and I have to speak a lot about all about the Rectenna, rectifying antenna technology. At first, I'd like to introduce an overview of the Rectenna as a receiver of the wireless power. It's a special technology only for the wireless power transfer. You have the good transmitter technology, for example, for the wireless communication or remote sensing or the other. And of course, you have the very excellent beamforming technology for remote sensing or MIMO or the other. But Rectenna, rectifying antenna is only for the wireless power transfer. So I focus on the rectifier technology. And I classify the 4 parts of this talk. And at first, I'd like to introduce normal theory and technology to how to design the high efficiency as a receiver at optimum input power. So this is the most basic theory and technology and the most important theory and technology for the rectifier. And some of you are interested in the energy harvester. Energy harvester means like a wireless power transfer, but a little bit different from the wireless power transfer. We gather ambient radio wave, for example, from your pocket, Wi-Fi or a mobile phone or TV or the other ambient radio wave. We can gather and we can convert this ambient radio wave into the electricity. For this application, we need a low power rectifier, Rectennas. So it's one of the most important topics to how to design the high efficiency Rectenna at the low power input. And on contrary, some of you request more power like a solar power satellite. For example, some of you request us to use over 1 kilowatt to fly the drone, for example. For this application, we need a high power rectifier. So today, I classify the theory and technology of the Rectenna into these 3 parts: optimum input, and low power, high power, and I conclude my talk. And this is a simple overview. Of course, Professor Nuno Carvalho has already mentioned. This is a simple structure of the Rectenna, rectifying antenna. This Rectenna consists of the antenna and rectifier. And in the rectifier, we sometimes use the diode, or some of the research applies CMOS or the other. And we combine the low-pass filter and output filter to increase the efficiency. This is a very simple diagram of the Rectenna. And Rectenna, this word was invented by William Brown. Maybe you know, William Brown is one of the scientific giants of the wireless power transfer in the 60s. He named it Rectenna, rectifying antenna, And this is his first patent of Rectenna. And of course, he develops excellent Rectennas with a new novel gallium arsenide diode was the other, and he carried out a lot of excellent WPT experiment. If you visit YouTube, you can find his excellent memorial experimental movie on the YouTube. Please check it. And this is the first patent by William Brown in 1969. And Rectenna, as I mentioned, consists of the antenna and rectifying circuit. It's very simple. And for antenna, of course, as you like, you can choose the antennas. For example, historically, William Brown chose dipole. It's very simple. Of course, now we can apply the dipole antenna for the Rectenna. And the other group applies the Yagi-Uda antenna or monopole or spiral antenna. And recently, a lot of people choose microstrip antenna. And the other people sometimes choose parabolic antenna, for example. And of course, it was not a real parabolic Rectenna with a parabolic antenna yet, but maybe in next year, we Japanese choose this Rectenna with a parabolic antenna to receive the power from the satellite. We will launch small satellite for the wireless power transfer experiment in next year. And from the satellite, from the low Earth orbit about 150 kilometers above, received power at the ground will be very small. So we will choose the Rectenna with a parabolic antenna. For example, you can choose it as you like. Of course, rectifier. In the morning, some discussion. There was some discussion. We can choose every rectifier, half-wave rectifier, full-wave, bridge, or the single shunt, or double R, or charge bomb. Of course, for your aim, you can choose the rectifier as you like. But important point for the wireless power transfer is theoretically 100% Rectenna should be used, should be developed for the wireless power transfer because we need very high efficiency. It's electricity. So compared to the wireless communication or remote sensing, we have to focus on the high efficiency. It means theoretically 100% is the most important to design the rectifier. Of course, it depends on the application, but usually our aim is to design the rectifier, Rectenna, whose efficiency is theoretically 100%. And this is a typical characteristic of the RF-DC conversion efficiency. Professor Naoki has already mentioned in the morning, and it depends on this real VI curve of the diode. So it has voltage, junction voltage in the real diode, and we have the breakdown voltage in the diode, in the real diode. So at the low input power, there are the region of the junction voltage, and the diode is not a diode in the low power. And if we input the high power, breakdown occurs in the diode, so efficiency just decreases. So here you can see we have an optimum input power to realize the highest conversion efficiency at the Rectenna. So this is the most important part. So today I classified my talk into optimum area, low power area, and high power area. So here you can see, now my explanation is based on the input power characteristics, but it's the same as a connected load, user load. If we connect the high impedance, efficiency decreases, and if we connect the low impedance as a user, efficiency decreases. It's the same. So diode, Rectenna is one of the power source with a very low internal impedance. So it's a little bit difficult device to keep the same voltage of the rectifier. So it depends on this VA curve diode. So sometimes after the Rectenna, after the rectifying circuit, we add, for example, DC-DC converter like a buck burst converter. This is developed in Kyoto University. So with help of this buck burst converter, we can change this characteristic of the RF-DC conversion to the unified characteristic. For example, so this is a very interesting approach in my university. And from here, this is a school. So I'd like to introduce a theory and technology of the high efficiency rectifier at optimum input power. So it's easiest way how to design the rectifier with a high efficiency. So around here. So originally, as I mentioned, you can choose the all rectifier as you like. But one Japanese famous professor, Ohira, calculated the theoretical limitation of each rectifier of the single shunt and a single series, single shunt, and bridge type, and voltage doubler, and double current rectifier. And based on his paper, he estimated the theoretical limitation of each rectifier. And as a result, based on this his theory, single series and a single shunt rectifier can reach approximately 81% as a RF-DC conversion efficiency, and a bridge type or the doubler type, they can reach approximately 90 and 92% as a theoretical limitation. It's his theory, but there is no doubt in this theory. But he only lacks the higher harmonics combination theory. This is only the RF-DC conversion only. And when we consider these waveforms as a diode, higher harmonics occurs. And maybe you know how we increase the efficiency as a transmitter. Maybe you know class A amplifier, class B amplifier, class C amplifier. But theoretically, class B amplifier reached only about 80%, because in the amplifier, there are no consideration about reuse of the harmonics. And additionally, we at the class F load at the output filter, we can reuse the harmonics to increase the efficiency, and theoretically, class F amplifier reached 100% conversion efficiency from DC to RF efficiency. So, for example, this is a real measurement data of the harmonics from the rectifier. It exactly meaning from the diode. So here you can see it depends on the input power, but there are some harmonics, second harmonics and third harmonics of the other from the waveform of the diode. So on the Professor Ohira's theory, he missed this re-radiation of the higher harmony. So unfortunately, he reached only maximum 22%, even at the bridge diode. So we have to consider how to increase the theoretically efficiency to the 100%. So solution is to reuse this higher harmonics to the electricity. So this is a very simple theory to reuse the higher harmonics as a rectifier. This is originally from William Brown and New York University's group in the end of the 70s. So in this rectifier, it mainly composed of the diode series in parallel and quarter length distributed line, and at last capacitance. the combination of the quarter length distributed line and the capacitance, and if capacitance is enough large, it's easy to calculate the impedance from the output side. This equation, maybe you know this equation as the characteristic impedance. And when capacitance is enough large, this seems to be open for orthoharmonics and short for even harmonics. So combination of this relationship of the impedance for orthoharmonics and even harmonics, as a result, this will be the full wave rectification with one diode. So please imagine when we add this quarter length distributed line and capacitance with a very large capacitance, we can create this relationship of the harmonics. And as a result, we can create a full wave rectifier only with one diode. But one problem is here. We need enough large capacitance to create this relationship. But if we add enough large capacitance, we can create a theoretically 100% rectifier only with one diode. So here we use the harmonics to increase efficiency. This is the original theory from the William Brown. And so waveform at the diode is here and here. So this is the waveform of the current, and this is the waveform of the voltage at the diode. So some of you know this waveform is exactly the same as a class F amplifier at the FET. So this one. This is an ideal class F amplifier waveform. And maybe you know this is a waveform of the class A amplifier and the class B amplifier. And theoretically, class A amplifier and class B amplifier cannot reach 100%. But if we install the output filter of the combination of the harmonics, we can waveform is zero, and theoretically 100% we can reach at the transmitter. This is amplifier theory. So when we consider how much harmonics we apply for transmitter, this is a theory of the transmitter amplifier. And if we apply the infinity even and harmonics, theoretically we can reach 100% of the power conversion from the electricity to microwave. This is a transmitter theory. But this explanation is the same for rectifier. When we apply the even and odd harmonics to increase the efficiency based on the Professor Ofira's theory of the single shot, we can increase the theoretical efficiency up to 100%. So it's the same. So this explanation for the transmitter of the class F amplifier can be applied for the rectifier for the single shot rectifier. So this is a basic theory of the rectifier, and especially for the single shunt rectifier. And we, Kyoto University, changed mind from the capacitance to the class F load to realize the high efficiency rectifier. Instead of the capacitance, large capacitance, we installed this quarter length distributed line, and we create the relationship of the impedance for even more than the odd mode. So as a result of the reuse of the even harmonics and odd harmonics, we can increase the efficiency, theoretically 100%, but in the real we develop. Unfortunately, efficiency cannot reach 100%, but concept is very good, I think. This is, we named it a class F amplifier. So I explained a lot. We can apply the transfer technology theory to the rectifier. So I now introduce class F amplifier. So in the other group, developed the other rectifier, for example, class C amplifier, and class D, class E. There are a lot of interesting rectifier with the same name of the transmitter, class C, D, E, F. Of course, class A or class B rectifier we can develop, but theoretical limitation is very poor for the class F or class B. So we choose mainly class F amplifier. I recommend you, but the other group develop class C, D, E rectifier, for example. So I recommend you how to increase the efficiency of the rectifier. It's very simple. Think amplifier design. Especially, I recommend you to apply the class F design for rectifier to increase the efficiency at the optimum input power. So this is a theory and technology of the rectifier at the optimum input power. And it's the same. For example, Professor Zoya Popovich group, University of Colorado, developing very, very interesting rectifier with combination of the amplifier. So originally, her technology is an amplifier technology. But she changed the input and output like this. As a result, this amplifier is applied as a rectifier. So at first, she develops an amplifier, but she changed the use of the input and output. As an amplifier, for example, efficiency of the PAE, power output efficiency, was 83% in her paper. And as a rectifier, RF-DC conversion efficiency reached 85%. It's the same circuit. So as I explain you again, think amplifier design. And if you can develop a good amplifier, it becomes suddenly rectifier, for example. So this is a very interesting approach from the University of Colorado. And additionally, so Professor Nuno Carvalho mentioned, we don't have any ideal diode. So we have only a real diode with internal resistance, internal capacitance of the other. And this is the other scientific giant, Professor Kai Chan of the University of Texas A&M. In 90s, he needs this theory to estimate the efficiency with a real diode. So based on this equivalent circuit of the diode, it's easy to estimate the efficiency with a real diode. So it seems a little bit complex, but if you have Excel, it's easy to estimate the efficiency with this real diode with this equivalent circuit. Please try it. And based on his theory, based on his formula, in this paper, he showed us this efficiency curve with the parameter of the omega RC. R and C is the internal resistance and the internal capacitance of the rectifier, of the diode. And if this omega RC figure of merit is very small, efficiency is close to 100%. But when we increase this omega RC figure of merit, efficiency decreases. It means you always mind internal resistance to consider the efficiency of the rectifier. So in this meaning, there is no doubt. If internal resistance R is bigger, efficiency decreases. It's very simple. But please don't forget, internal capacitance is the same importance to how to control the efficiency. And additionally here, omega. So of course, it's easy to estimate. We consider the capacitance as j omega c over 1. No, 1 over j omega c. So this figure indicates when we increase the frequency, efficiency of the rectifier decreases. So in this figure indicates three important characteristics of the efficiency of the rectifier. We have to choose low R internal resistance diode, and of course we also must choose low internal capacitance diode, and additionally lower frequency is better to realize a higher frequency. So this is originally from Kai-chan and his group theory. And so this is a real data of the rectifier developed in the world. So here you can see when we increase the frequency based on the Kai-chan's theory, efficiency decreases. It's very simple. And this additionally, output power decreases. It's a common theory and development of the semiconductors. So when we increase the frequency, efficiency of the rectifier, so additionally transmitter decreases. So in the morning we have some discussion, higher frequency is better or not. If we increase the frequency, of course, based on the antenna theory, beam efficiency increases, or we can keep the smaller antenna with higher frequency. It's an antenna theory, there is no doubt. But if we increase the frequency, circuit efficiency of the rectifier or the transmitter amplifier decreases. But I think which is better, higher frequency or the lower frequency? Beam efficiency depends on the Friis transmission formula and the Maxwell's equation. We cannot control it. So we have only three parameters: size of the antenna, frequency, and distance to estimate the beam efficiency. And there is no engineering, I think. I will explain later. But when we have a good engineering to develop a very good semiconductor, diode, HEMT, or other, we can increase the efficiency, circuit conversion efficiency when we increase the frequency. So in this meaning, higher frequency is better because we can increase the efficiency of the diode or efficiency of the circuit. It's an engineering. But antenna, it depends on the Friis transmission formula, and we cannot control. So I recommend to use, or as a new novel study, is to increase the efficiency. So it's my recommendation. And so additionally, this is a circuit theory, and we have to consider the impedance matching. And based on the equivalent circuit of the diode, we can estimate the input impedance of the diode like this figure. And when we change the connected load or input power, this impedance of the diode changes. It's a normal theory. And this is measured data when we measured data of the RF-DC convergence and reflection when we change the connected load. For example, here it's the same. Here is the optimum RF-DC conversion efficiency when we match the impedance and when we match the input power or the connected load. But when we change the connected load, input impedance, input power, even if low input power or low connected load or high impedance or high input power, reflection occurs because impedance unmatch occurs and efficiency decreases. So this is a simple theory of the impedance matching, and diode is not a linear device. It's a non-linear device. So even if we know where this equivalent circuit of the impedance, unfortunately, only one point we can match the impedance in the diode. So when we change these parameters, reflection occurs by the impedance matching and efficiency decreases. So this is we have to consider how to match the impedance and which input power of which connected load we must aim to realize a higher efficiency. And this is the same impedance matching theory. And based on this equivalent circuit on the Smith chart, we change these like this when we change the input impedance or when we change the connected load, etc. So matching point is only one here. It's very simple. So we have to consider when our aim to design the rectifier is the what connected load or what impedance, what input power. So this is a very important point, how to match the impedance. And it's a common theory. So this is a summary of the efficiency, how to increase the efficiency of the rectenna at the optimum input power. So first of all, we must choose theoretically 100% rectifier. So if we choose a half-wave rectifier, unfortunately, theoretically, we can reach only 50%. So we cannot overcome the theory. So please choose a theoretically 100% circuit. I recommend you use a single shunt because diode involves the resistance or the capacitance as a loss factor. So theoretically 100% we can realize with both bridge type or the single shunt rectifier. But please imagine, in the bridge, it involves 4 diodes with losses. So instead of the bridge circuit, single shunt rectifier, theoretically 100% is the same, but it involves only 1 diode with losses. So we have to consider how to reduce the number of the diode with losses. So this is a very important topic, I think. And of course, next we have to choose a diode. And as I mentioned, low omega RC. This is the other important point. Not only low resistance, but also low capacitance for the diode we have to choose. And match impedance, as I mentioned, and this is a circuit theory. And hopefully, design the circuit with a higher harmonics combination, like class F amplifier. So when we consider the class F amplifier, we can reach theoretically 100% rectifier. And additionally, we have to add the high voltage close to breakdown, because optimum efficiency is realized very close to the breakdown voltage. So this is very important to the next topic. When we consider when we design the rectifier with a higher efficiency at the higher voltage close to almost breakdown voltage. So this is a very important point. And additionally, we have to consider the combination of the antennas, because a rectenna consists of the antenna and rectifying circuit. So this is a summary of how to increase the efficiency of the rectenna rectifier. So from here, I'd like to explain the antenna technology for the rectenna. So this is a theoretical beam efficiency Professor Nuno Carvalho mentioned in the morning. Based on this equation, this is a free transmission formula without any assumption. Maybe you know, in the far field, in the far field, you always apply the free transmission formula. But for the far field, we must consider the assumption of the plane wave. But in the near field, radiative near field, there is no plane wave. So instead of the free transmission formula with the assumption of the plane wave, in the radiative near field, we must use this equation to estimate the beam efficiency theoretically. And based on this Friis transmission formula without any assumption of the plane wave, we can reach approximately over 90% or 99.90%. So it depends on the same parameters, size of the antennas and distance and frequency. It's very simple. We cannot control it. So even if we realize a solar power satellite on the 36,000 kilometers above, when we realize enough large antenna, we can reach 99% of the beam efficiency. So this is a theoretical curve of the beam efficiency. But someone consider when we realize the beam efficiency close to 100%, but how about the beam receiving efficiency at the aperture of the receiving antenna? Some of you consider beam receiving efficiency at the receiving antenna cannot reach 100%. Usually, theoretically, 50% is the limit of the receiving power at the receiving antenna. So this is a right or wrong, I think. So theoretically, we can realize 100% of the receiving antenna in the case of the array antenna. So in the case of the one antenna, one element only, your understanding is correct. Usually we can reach 50% only as a receiving antenna theory. But when we apply the array antenna as a receiver, we can reach 100% of the receiving power at the receiving antenna. I'll explain the theory. So this is based on the normal array antenna theory. This is not a rectenna theory. This is originally from the phased array antenna theory, maybe in the 40s or 50s. And when they consider this antenna, slotted antenna array, it's infinite arrays. And when we consider this slotted antenna array, based on this calculation, maybe I cannot explain the detail in my talk. And so this calculation of the impedance matching theory between the antenna and space. And as a result, this we can reach this efficiency, theoretical efficiency in the array antenna. And as a result of this calculation, a formula to estimate the antenna receiving efficiency, when we choose the direction of the receiving beam and element spacing. And around here, we can reach 100% receiving efficiency as an array antenna. Of course, it means we have to develop the very closed antenna element in the array antenna up to one lambda. And when the beam is transmitted to the bent direction. For example, theta is 30 degree or 45 degree. Efficiency cannot reach 100%. But when we choose optimum beam direction and optimum element spacing, theoretically, we can reach 100% based on the impedance matching theory with antenna and space. So the other Japanese estimated the same theory with a microstrip antenna, for example. And he reached a very similar formula like this. And as a result, in this paper, unfortunately it's only Japanese, but he reached the same result. We can reach a theoretically 100% without any loss in the antenna. And in his paper, he stores a loss factor in the antenna. And of course, if we have a real loss in the antenna, we cannot reach a 100% efficiency. It's natural. But if we consider the antenna without losses, theoretically we can receive 100% microwave beam at the receiver. So this is a very, very important theory because some antenna researchers consider we cannot receive the 100% wireless radio wave beam at the receiver antenna. 50% is a limit. Some famous antenna professors consider. But based on this theory of the impedance matching with the space and the array antenna, we can reach 100% as a receiving antenna theories. So this is just a theory. So in my university, we try to simulate this situation. So we put a dipole antenna with a reflector, and we transmit the microwave power in front. And here is a simulation result. At first, this radio wave microwave is propagating into the receiving antenna. And this is reflected radio waves. And at first, some small impedance unmatch occurs, and some reflection occurs. But here you can see there is no reflection. So my student estimated the receiving efficiency reached approximately 99.9%. This is a simulation result of the FDTD computer simulation. So based on the theory, the simulation result is the same. We can receive the 100% radio power at the receiver. So beam efficiency reached 100% based on the Friis transmission formula without any assumption. And receiving theory, as I mentioned, we can realize 100% theoretically RFDC converter efficiency. And we can, now I show you, we can receive the 100% efficiency at the receiver. So except the transmitter, we can realize a 100% efficiency from the transmitting antenna to the final electricity via receiving antenna and the receiving side. So this is a theory of the rectifier, rectenners. And the other Japanese try to carry out the experiment. So he develops an antenna. They can change the element spacing. For example, here you can see there is a cutting point, and he carried out. At first, he estimated the finite array theory. I explained the infinite array theory as a 100% receiving power, but the other Japanese, estimated the impedance matching in the finite arrays. Of course, if we consider the finite array only, we cannot reach 100% because H problem. But based on this theory, he carried out the experiment. And so when they change the element spacing and the other, and here you can see it's an experiment. So unfortunately, they cannot reach 100%, but over 50%, they receive the microwave power at the receiver. So in this meaning, we can overcome 50% at the receiving antennas. So please believe me, we can receive 100% microwave power at the receiver as an antenna. So this is a Japanese result. So theory, simulation, and experiment. So next, we have to consider, I'd like to show you the recent, very interesting rectenna, excellent rectenna with a high efficiency. So this is our result, Kyoto University result. One of my PhD student developed the 91% at the UHF 920 megahertz, and he considered how to match the impedance without any impedance matching circuit, because impedance matching circuit involves a loss factor. So he proposed this impedance matching circuit around the diode, and he reached 91% at the UHF frequency. I think this is one of the world record of the RFDC conversion efficiency at the UHF. And this is the other Japanese group. This is a very high power rectifier to drive the drone of the other. And this is old matter, but they reached 91.6% at S band. And this is a Rectenna array. So I think this is a very interesting rectifier. There is no detail because of some secret matter involved, but this is the highest efficiency at about 10 years ago. And recently in my university, the other PhD student succeeded to develop the 91 efficiency with the gallium arsenide diodes at the S band, for example. And Kanazawa Institute of Technology, Japanese famous university, developed the very excellent efficiency 90.2% at the S band with 10 watts. And they like the bridge type diode, a bridge type rectifier. And same group develops a C-band rectifier with the highest, with high impedance technology. I will explain later. But they reached 92% at the C-band, 5.8 gigahertz. I think this is a world record at the C-band rectifier. And they developed a MMIC rectifier at the same C-band, and with the MMIC technology, they reached about 98% as a conversion efficiency at the C-band. And my group develops same MMIC at 24 gigahertz. And at that time, about 10 years ago, we reached about 50% as a conversion efficiency. I think this is one of the world records at 24 gigahertz. And double band, 29 gigahertz rectifier. So efficiency is not clear in this paper, but this is a very interesting trial to develop the double band rectifier. And ratio, they have a very huge budget. So they developed the gallium nitride diode itself, and that's a double band, 29 gigahertz, and they reached about 6, there is no data around here. So they reached over 60% at the double band as a conversion efficiency of the rectifier. So this is a very great success to develop the double band rectifier. But input power, optimum power is very low. I don't know why, but they developed the gallium nitride itself. But when they increase the frequency to the double band, so power is very small. But we have to check it. But my friend Homan Kazami successfully developed the double band rectifier with 61%. And now I think this is a world record of the frequency. Japanese group developed 303 gigahertz rectifier. Of course, as I mentioned, frequency increases and efficiency decreases. So efficiency is not good, but this is a world record of the frequency, and I expect the future work by themselves or by you to develop the very high efficiency rectifier, because we are engineers. We can overcome the theoretical limitation by the technology. So now it's a world record of the frequency, 303 gigahertz in the world. So from here, I'd like to explain the low power rectifier. Maybe some of you are interested in the rectifier for the energy harvester. So around here, we have to consider how to increase the efficiency. But as I mentioned, diode involves junction voltage in the normal diode. So we have to consider how to increase the efficiency at the, how to increase the low efficiency at the low power input. And this is one of the energy harvesting and one of the sample of the input power for the energy harvesting. So here you can see from the ambient radio wave, mobile digital TV or Wi-Fi or the other. Usually, we only receive the some dozen of the microwatt only as energy harvesting. So based on this low input power, unfortunately, efficiency is usually poor. So we need engineering, we need a good theory and technology to increase the frequency at such this low input power. So I will explain this technology next. So my friend, Professor Simon Hemura, summarized this historical view of the rectifier RFDC conversion efficiency and power in history from the mid of the 70s. And at first, William Brown as the other group developed the around the 1 watt rectifier. Of course, as I mentioned, this input power area is suitable to realize the highest efficiency for the normal Schottky barrier diode. But when we decrease the input power, for example, 1 microwatt and 1 milliwatt or 1 microwatt, efficiency suddenly decreases, as I mentioned. And but historically, this efficiency increases like this. But we could not reach the maximum power around the optimum input power 1 watt. But now this efficiency as a 1 milliwatt or 1 microwatt is increasing just now. And this is the viewpoint of the summary of the RFDC conversion efficiency and input power. And around here, as I mentioned, when we decrease the input power, efficiency decreases. It depends on the junction voltage of the diode. As a viewpoint, when we change the frequency, and my friend summarized this view with a developed diode, developed rectifier for the energy harvester. So efficiency is poor around here. And as I mentioned, this Rectenna consists of this antenna and rectifier, and we have some way to increase the efficiency at the low input. So at first, easiest way to apply large antenna. So there is no explanation. So it's easy, but it's not interesting. I will explain later. And as an engineer, most interesting point is how to increase the efficiency with the circuit technology or the semiconductor technology. And we have the other way to increase the efficiency. These are only the time wave only and 1 frequency. But for the energy harvester, we can expand the frequency from the modulated wave or multi-tone wave or the other. So this is the last technology to increase the efficiency with a wideband rectifier. So I will explain in order. So this is antenna technology. Of course, large aperture antenna is a large real aperture antenna. So there is no doubt. So if you can develop the large antenna, we can gather the more input power into the circuit. So we don't have to develop the special rectifier. But it's not convenient for mobile, because if we need, for example, 1 meter antenna to gather the ambient radio wave from the microwatt per square meter. So as a mobile technology, I suppose all of you don't bring this large antenna. So the important point is this. Large aperture antenna is the approximately same as a large rear aperture antenna. It means when we bring smaller antenna with large effective aperture, it's very interesting antenna for the energy harvester. So it is called the super gain antenna. Small antenna but large aperture, large effective aperture. But I look for the super gain antenna. I found these antennas. For example, Yagi-Uda antenna is one of the super gain antenna. From the front, antenna size is only the right. But front and the back, we install the other reflector, the other effect of this extra antenna. We can increase the aperture area of the Yagi-Uda antenna. So in this meaning, Yagi-Uda antenna is one of the best super gain antenna. But only in front, we only see the line only. But we need a thickness with this reflector or conductor. So in this meaning, Yagi-Uda antenna is best or not. We need the other technology. Of course, some of you are developing microscope antenna with thickness, very thick base. Of course, we can increase gain of the microscope antenna with a thick base, but it's the same. We need a thickness to increase the gain of the microscope antenna. And one of my Ph.D. students super gain antenna with a combination of the higher harmonics in the resonator. But theoretically, we can increase the gain of the antenna only with a very, very small resonator. But in the real, we cannot realize this resonator antenna with a higher harmonic combination. So in this meaning, we could not develop the super gain antenna with this technology. And some of you consider we have a meta surface. Of course, we can apply the meta surface or the lens antenna, but only for the antenna, we can gather a very wide area radio waves through the meta surface. And in this meaning, this antenna is a super gain antenna. Antenna size is the same, but in the real, we must put the large size of the real meta surface. For user, it's the same. If we bring the large antenna or if we bring a large meta surface, it's the same. Theoretically, it's a super gain antenna, but the meta surface of the lens antenna, it's not suitable for mobile, I think. So unfortunately now, in my understanding, there is no good super gain antenna in the world, historically on the current. So to increase the aperture of the antenna, only in the paper it's best. But for the real application, it's not suitable, I think. So, and we have the other problem if we choose a large aperture antenna, because it's very simple, it's a school. So large aperture antenna is equal to realize a high gain antenna. And the high gain antenna is a narrow directivity of the antenna. It's very simple, maybe you all know. It means when we install the large aperture antenna and it's a high gain antenna and narrow directivity, for energy harvester, we would like to gather the ambient radio wave from the everywhere. But when we install this high gain antenna and narrow directivity antenna, we have to control the antenna direction to gather the enough ambient radio wave. So in this meaning, this is not suitable for the energy harvester from the ambient radio wave. And additionally, this is an extra comment. Usually, I think EIRP is an illusion because so for the wireless communication group or remote sensing group, you always use an EIRP. transmitting power multiplier antenna gain. And when we consider the 1 watt transmitter, but we apply the 10 dB antenna. So as a EIRP, it's a 10 watt transmitter. You always consider, but we only create 1 watt as a power. So we have a law of the conversation of the energy. So 1 watt is a 1 watt, not 10 watt. But EIRP explain it's a 10 watt transmitter, sometimes. So I don't like it. 1 watt is a 1 watt. Please don't use the concept of the EIRP for the wireless power. We have to consider the law of the conversation of the energy. So we cannot increase the power except the transmitter amplifier. But after the transmitting antenna, we cannot we cannot increase the power. So, please don't. I recommend you to use EIRP concept for the wireless power transfer systems. And so now I explain the antenna technology for the low power rectifier. But unfortunately, there is no super gain antenna. So next, as an engineer, we have to consider how to increase the circuit conversion efficiency. And first of all, diode is most important technology. And now this original explanation by my friend Simon Hemura, and he showed us the current limitation to explain the rectifier, to explain the diode, suitable diode for the rectifier. By the current limitation, efficiency can explain this formula. So in this formula, you can find some parameters. And for example, how to increase the efficiency, we can increase the junction resistance in his explanation. And it means it's a higher Schottky barrier or high Q matching circuit. And the other parameter, for example, here, and increase the non-linearity. And my friend Simon recommends us to apply the tunnel diode, spin diodes, or additionally low temperature. And we have the other parameter, and increase the input power. This is not, we don't have to explain more. Increase the input power, there is no engineering. So, but this new expectation, my friend showed us, tunnel diode or the spin diode instead of the Schottky barrier diode is suitable for the low power rectifier. And my friend, so Simon, summary, the evaluation of the diode technology over the years, and Schottky barrier diodes, we can, year by year, we can increase efficiency close to 100%. But instead of the Schottky barrier diode, some professor tried to develop the low power rectifier with tunnel diode or MIM diode or spin diode. And this is one example. Of course, as you know, tunnel diode will be the negative resistance when we add the higher voltage. But before the turning point of the negative resistance, tunnel diode is still diode, and the Professor Manev develops a very good low power rectifier with a tunnel diode. Here is a comparison with a single Schottky barrier diode rectifier and a tunnel diode rectifier. And around this area, so efficiency is higher than with a tunnel diode than the Schottky barrier diode. Of course, around here, efficiency supports negative resistance, of course, around this area, high voltage area. But at the low power area, we can apply the tunnel diode. This is one example. So instead of the Schottky barrier diode, we can apply the tunnel diode, the spin diode, for example. But if we don't have enough budget to develop a good diode, we have to consider the circuit technology. So if we don't have a good tunnel diode or a good Schottky barrier diode, the other circuit technology help us to increase the efficiency. So usually for the energy harvester or for low power rectifier, some of you develop charge pump or Cockcroft-Walton high voltage circuit. Of course, sometimes it is applied for the energy harvester. But here you can see there are a lot of diode with a loss factor. And in this figure, it's easy to understand. We can increase the voltage in this circuit, but we cannot increase the efficiency. Only what we can is to increase the voltage to drive the, some device as a user. So charge pump itself is a very good technology to create a high voltage, but I think this is not good to realize a high conversion efficiency at low power. So please go back to this design theory. How to add the high voltage, hopefully almost breakdown voltage, even at the low input power. So there are a lot of trials with a normal Schottky barrier diode to add the voltage at the diode, even if microwave input power is low. So there are some approaches: self-bias voltage, input impedance matching at the low power area, or high impedance circuit technology, or reuse of the reflected microwave, differential rectifier, or the rectifier with a resonator, and selective matching circuit, as introduced in order. So, of course, some of you consider when we add the extra voltage, so it's easy to overcome the junction voltage. But please consider, rectifier is a rectifier without any battery. So, of course, for the receiver, for the microwave wireless communication, we can add the extra voltage at the receiver side. But usually for the WPT system, user requests power from the outside only. So the professors of the University of Canterbury proposed self-biased and self-synchronized rectifier. They reuse some power of the reflected microwave at the rectifier to add the voltage. So this is a very interesting approach to increase to overcome the junction voltage without any extra power source at the users. So this is a very one of the interesting technology to increase the low power efficiency. Impedance matching is a very important technology to increase the efficiency at the low input. And for example, MIT group proposed, this is additional but important, active input impedance matching circuit they added. And as a result of this active impedance matching circuit, they can increase these areas' efficiency. So now they change the impedance matching in each input power, and as a result, they can increase the efficiency, for example. And in Kyoto University, we all output filter side. So of course, at the output filter, we can match impedance at the low input power, and we optimize the impedance matching at the low output filter, and as a result, we can increase efficiency at the low input microwave power. For example, this is the same input matching technology at the output filter side, for example. And this is the same output filter matching. Usually, as I explained now, we use a quarter length distributed line and class F load or capacitance. But in this rectifier, we use only 0.1 lambda output filter length to increase the efficiency at the low input power. So this is our try. And reuse of the reflected power. One one Japanese university's professor developed this interesting rectenna. So at the output filter, some reflection occurs. Some reflection means that it's a fundamental frequency. And they reuse this reflection of the microwave at the output filter, and they increase voltage at the diode. Theoretically, maximum double voltage we can add it. So it means we can increase voltage at the diode. And my university proposed and developed a feedback rectifier. And we reuse the reflected wave again. And we add this reflected wave again, and we increase the efficiency. So we tried some kind of the feedback loop rectifier. For example, this is only one rectifier with a feedback loop from the diode, and this is a combination of the two rectifier to increase the reflected wave, and we the three rectifier type to reuse the reflected wave. For example, so to the reflected microwave, we can increase the efficiency at the low input power, for example. And the other approach is a differential rectifier. A differential means, for example, this is a very historical rectenna in Japan. And from this, they put the microstrip antenna. And from here to here, they use the one is normally positive microwave here, and from here, it's easy to understand. From here, this is a negative microwave flow in this area. From this positive and negative at the diode, we can increase voltage at the diode double, for example. So this is a very good rectenna to apply the combination of the antenna and rectifiers. This is a very old matter, about 30 years, 40 years ago in Japan. So this is named one of the differential rectifiers. And in the circuit, the other Japanese group develops a rectifier with a rat race. Concept is the same. They apply this differential circuit only at the antenna, but they develops a rat race with combination of the negative line here, and at last we add the double voltage at the diode, for example. And the other Japanese professor developed two antennas differential rectifier, for example. From here to here, positive and negative microwave added this diode, and as a result, double voltage added in this diode, and they can increase the efficiency at the low input power. This is a very interesting approach of the differential rectifier. And this is the other to increase the voltage with help of the resonator. It's very simple. When we add the resonator, we can increase the voltage. So he develops a rectifier with a quarter-length distributed line resonator at UHF band, and he realized about 40% at minus 20 dBm with help of the quarter-length resonators. And the other group add the directory resonator with LC or D electric resonators after the diode. It's very simple, but in the real picture, this D electric resonator seems to be big. So approach is very interesting, but they can increase some efficiency around here. But in this case, the size of the D-electric resonator is large, what we think. But it's a very interesting approach to add the voltage at the diode, even if microwave input power is very low. And this is a last approach. So selective matching circuit like a Doherty amplifier. They apply the two rectifier system, and before the rectifier, they change the matching impedance depends on the microwave power. And at the higher input, they use this higher powers rectifier, and at the low power, they apply the low power like this. So with combination is a low power and high power with this matching circuit, selective matching circuit, and they can increase this efficiency. And here, Professor Kenjiro Nishikawa summarized this selective matching circuit in the last WPMc Asia Pacific Microwave Conference. And we can read it on the IEEE Explorer. And he summarized this selective matching circuit or selective matching circuit rectifier. So please check his proceedings of the WPMc 2023. So, and this is, I think this is the most suitable rectifier for the low power for the low power input. As much a high impedance circuit and a high impedance antenna. Of course, it's easy to understand when we consider when we develop the 50 ohm circuit. Voltage is, for example, 1 voltage. But when we increase impedance, for example, 5 kilo ohm, we can increase this voltage up to 10 volt or more at the diode. It depends on the circuit impedance. So, Kanazawa Institute Technology Group develops a 1.6 ohm antenna and circuit for the low power micro rectifier, and they can increase efficiency at a very low power area. So this approach, high impedance circuit and high impedance antenna, are most suitable, I think, to increase efficiency at a low power input. So this is the last method to increase the low power, to increase the efficiency at the low power input. Frequency region, we have to expand the frequency or time. So of course, we can gather dual frequency or triple frequency or the other. So this is a very historical dual band rectifier, 2.45 and 5.8 both. This is developed by the Kai-chan. And this is a triple band or the other. And at last, this is the broadband rectifier for energy harvesting. This is developed by the University of Colorado. She developed a very wide band rectifier from 2 to 18 gigahertz rectifier, she said. When we expand the frequency, of course, received power increases, and as a result, we can increase the efficiency. And she continued developing this system, and about 5 years ago, he showed us the developed octave bandwidth RF energy harvester on the T-shirts, for example. So this is a very interesting rectifier, Rectenna, for the energy harvester. And the other group, University of Liverpool, develops a high impedance and a wideband rectifier like this here. So this is a very interesting rectifier, wideband and high impedance matching, developed by the University of Liverpool. And these are mainly the antenna technology. They can expand the frequency range at the antenna, but we have to consider how to expand the frequency range at the circuit. So one of my friend, Professor Apostol, has developed once broadband matching circuit as a matching circuit. This is based on the broadband bandpass filter theory. But with help of this band pass filter theory, they can expand the frequency range up to 400 gigahertz to about 1 gigahertz, for example. This is a circuit approach to expand the frequency range. So we like to develop the output filter. So at the output filter, we developed a class F rectifier, but class F rectifier cannot apply the wideband rectifier because we use a combination of the higher harmonics. So we developed this wideband class F load sector type, and we can expand these resonation frequency for each harmonics, and we can expand the frequency a little compared to the previous class F rectifier. So these are very interesting approach. And additionally, if we control the transmitter, so as Professor Naoki mentioned in the morning, pulse or the multi-tone microwave is better. In the frequency region, when we apply the pulse or multi-tone, frequency range becomes wider. But when we add, for example, pulse to the rectifier, average power is average RF power is the same, but peak voltage becomes higher. So as a result here, you can see we can change the duty ratio in the same average microwave power, and we can increase the efficiency like these figures. So this is a very interesting approach, and the multi-tone is more interesting, I think. So these are approaches to increase efficiency at the low input power. So it's the end of my one part of my talk, low power rectifier. And from here, some of you user request more power to fly the drone or to realize the solar power satellite or the other. In this case, on contrary, we need a high power rectifier. So this is the last topic in my talk. So around here, of course, in this case, we have to consider the breakdown voltage. So, of course, it's easiest way to increase the efficiency at the high power is to use a high power diode, wideband gap diode, if we have, or to divide the input power by circuit or by antennas. This is a last method. Please consider apply microwave tube for the high power application. So I'd like to explain in order. So wideband gap device to increase the power as a receiver. And of course, at the microwave frequency, we usually expect the gallium nitride mainly. Of course, we have the other wideband gap diodes, silicon carbide or gallium oxide or diamond or the other. But recently, we have mainly the gallium nitride as a commercial devices. For example, this summary of the gallium nitride devices now we can buy in the world. Ampleon or the inauguration or MPX or the other. And but this is mainly the HEM or HBT for the transmitters. So of course we can apply the three-port devices instead of the diode. But this is mainly this is not a diode. So of course when we buy these three-port devices, HEM or HBT, to develop the rectifier, but it's not the most suitable device for the rectifier because diode is the most suitable device. So instead of these HEM or HBT, some group try to develop the gallium nitride diode itself. So, for example, this is our trial with the help of the Japanese University, Tokushima University, about 10 years ago, almost 15 years ago. So, at first, professor of the Tokushima University developed this shape of the gallium nitride diode, originally by the FET structure. But this structure is very good so to rectify the high power microwave. And this is the developed parameter for the gallium nitride diode. And this is the characteristic. And this is a real developed gallium nitride diode. And we apply this developed gallium nitride diode for the high power microwave rectifier. And as a result, at that time, we realized about 74% at 5 watt input power at the S1. For example, this is a very old matter, but I think this is one of the first trial to develop the gallium nitride diode for high power microwave rectifications. And the other, next we developed the other shape of the gallium nitride. This was originally from the FET structure, but for the diode, we consider this simple shape N and P structure connected directly vertical, and based on this concept, we developed the other gallium nitride Schottky barrier diode. But unfortunately, theoretically, we can reach 71% at the 20 watt microwave input. But in the real, after developing this gallium nitride diode, unfortunately, efficiency could not reach a theoretical limitation, only 40%. This is our second trial. But the other group are trying to the gallium nitride diode for the high power rectifier, and we expect the next new gallium nitride diode for the high power rectifier. So if we don't have a good gallium nitride diode, we only have silicon Schottky barrier diode. For example, we have to consider how to increase the efficiency, how to keep the efficiency at a high power input. So in this case, it's very simple, and there is no secret. After the antenna, we can divide microwave power with the help of the power divider. So in each rectifier, we can reduce the microwave power into the diode. So we keep the high efficiency with the high microwave power. So this is our trial, but in the real, we developed it. For example, this is about 100 watt rectifier, only with one rectifier. But here you can see it's not beautiful. So we can succeed developing the 100 rectifier, and with the rectifier, we carried out a very high power WPT experiment in the room. But I fear this is not beautiful. So we need a good gallium nitride diode, hopefully. But we have the other way. This approach is to divide the microwave power after the antenna. So next we consider at the antenna we can divide the microwave power into each normal rectifiers, for example. So in this meaning, this is a technology of the Rectenna arrays. For example, these are developed Rectenna arrays in Kyoto University, S-band and C-band or the other. So when we increase the microwave power or the electricity at the user, a very good technology to increase the microwave power. But we have to consider, so as I mentioned, large aperture antenna is a high gain antenna, and it's a narrow directivity antenna. But when we consider the array, this concept is the same for the one large aperture antenna or large aperture antenna with a phased array. There is no change between the relationship between the aperture and the gain and the directivity for the antenna element or for the array technology. But only in the rectifier, Rectenna, this relationship does not be satisfied, because in usual phase to expand antenna aperture, this received microwave power added with information of the phase. So when microwave beam propagates to the other direction, totally with a combination of the different phases, received power decreases, so it becomes a narrow directivity. It's a normal theory of the array antenna. But when we put a rectenna as an array, here you can see in each antenna we put a diode. In this meaning, there is no phase information at the combination point. So in this meaning, as a result, so directivity of the rectenna array still wide. For example, this is a real estimation of the compared to the array antenna and rectenna array antenna. So it's very simple. When we put this antenna element with the directivity of the cosine theta, for example, and when we put this antenna with 13 elements, 50, 120 elements as an array, when we consider the normal array, directivity becomes narrow and narrow and narrow. There is no doubt. It's the same. When we increase the aperture of the antenna, directivity becomes narrower. But when it's very difficult to find it, but when we add when we consider the rectenna array, there is no information of the phase, and as a result, activity of the one element becomes as a directivity of the array rectennas. So in this meaning, in the rectenna array, we can expand the aperture of the antenna aperture in the rectenna array, but directivity is still the same as one element. So this is the effect of this amplitude combination after the diode. So in this meaning, when we increase when we increase the received microwave power, I recommend you to use the rectenna array instead of the one high gain antennas. And we can divide the microwave power into each rectenna additionally. So this is a very interesting theory to realize the rectenna arrays. Rectenna array can realize a large area, large aperture, but directivity is the same as one antenna. So this is a very interesting approach. And but after receiving the microwave power and after rectifying the electricity, we have to combine, because a user is only one user, and they require a very high power. So in this case, we have to consider how to combine the rectified DC power. Usually, there is no problem to add the rectified microwave power as electricity. For example, from the one rectenna, we receive the 1 volt, and the other rectenna creates a 0.5 volt. The other is a 0.3 volt. It's very simple. We can add these rectified microwave power as electricity. But as I mentioned, rectenna has this characteristic, and it has an optimum input microwave power and optimum connected load to realize the maximum RF-DC conversion efficiency. So this is the most simple equivalent circuit of this characteristic. So when we consider the rectenna is a DC source and internal resistance, and in this equivalent circuit of the simplest rectenna, we can realize this characteristics of the RF-DC conversion efficiency curve. So it means when we put the same resistance, same impedance at the user, we can realize a maximum efficiency. But when impedance at the user becomes higher or lower, unfortunately, efficiency decreases. So based on this simplest equivalent circuit of the rectenna, we can consider how to connect the array, rectenna as an array. Especially, how do we connect the rectennas in series or in parallel? Usually, it's easy to understand there is no difference between the in-series connection and the in parallel connection. But in the experiment, showed us some difference occurs in the series connection and the parallel connections. So this is originally explained by the University of New York in the end of the 70s. And they used this circuit of the single shunt rectifier, and they consider these figures, VI curve or a series or parallel connection. After we connect the rectennas in series or in parallel, what happened in this VI curve. So based on this excellent past experiment, past theory by the New York University, we Kyoto University carried out and experiment, and we read some theory how to combine the rectennas in series or parallel, which is better. It's my PhD thesis. So when we change at first, when we connect rectennas in series or in parallel, it's easy to understand. Optimum changing, shifting to the based on these figures. So in series, optimum impedance as a user, so sum of the internal impedance. It's very simple. And if we connect the parallel optimum impedance to realize the maximum efficiency decreases based on this parallel connection. So we carried out this experiment, and we reached the normalized resistance in series and in parallel, and this is the current, voltage, and the DC power, rectified power. And when we install the normalized resistance, and the experimental result match the same characteristic. It simplest equivalent circuit is correct, I think. So at first, based on the simplest equivalent circuit, we checked the change of the efficiency characteristic, and next we consider which is better in series, in parallel, to realize a high efficiency. So we carried out the experiment at first, and we put two rectennas in this tapered microwave beam pattern at near field, radiative near field. And when put, for example, rectenna around here, input power is very high, and the other rectenna is around here, input power is low, and when we connect these two rectennas in series or in parallel, how much power we receive. We carried out this experiment in my PhD thesis, like this. And we change the position of the one rectenna, and we change the ratio of the input power in each rectennas. And as a result, it's an amazing result when I was a PhD student. In series, efficiency, I don't know, power, total power of the receiver, rectenna decreases compared to the parallel connection. So this is a ratio between the normal addition, this is a normal compare ratio between the combined power and simply summation. So as a result, so in parallel connection, we keep the same power if we connect the electricity just after the rectifier, or independent we measured, and next we combine the later. But in the series connection, total power of the combined electricity decreases. So in my student time, why this difference occurs in parallel is better, or in series, unfortunately, total power decreases. So this is a very similar explanation by the New York University. So this is input power and load resistance, and contour indicates receiving conversion efficiency. And when we put the two rectangles and in series and in parallel, this point to explain the rectifier, how to change this circuit combination. So in this figure, so for example, if we connect the parallel, this receiving characteristic point, move to this line, and in parallel, voltage should be the same, because this is, please go back to here. So in parallel, it's very simple. It's a Kirchhoff's law. In this connection, these two rectenna source should be the same voltage. And in series, current in each rectenna should be the same. So in this meaning, there is no I missed. This is a voltage characteristic and a current characteristic. So when we connect in parallel, voltage should be the same. It means at first, independently, this rectenna characteristic point was 0, but when we connect in parallel, voltage should be the same, like this contour map, and it moves to the other. So as a result, current moved to the changes. And in series, in this case, current should be the same, and as a result, voltage changes like this movement. So as a result of these different changes in series, unfortunately, this trend of the contour map is not suitable to keep the to keep the good output power. But because this contour map a little bit bent to this area, so in series, unfortunately, when the current should be the same, unfortunately, total power decreases. And in parallel, so voltage should be the same, and as a result, the change of this characteristic point is very close to this bend curve, and as a result, a change is very small. So we think in this meaning, common voltage is for the to keep the high output power in parallel connection. But in series connection, to keep the high output power in the Rectenna array. So as a result, we have to consider how to consider the best connection in the DC after the rectifying circuit. In this meaning, in series and in parallel, of course, in parallel connection is better, but we usually need the higher voltage. So in this meaning, we have to connect the Rectenna array in series to increase the voltage. So in this trend occurs when we consider the different input power, input microwave power to the rectifying circuit. So in this case, I recommend you to connect the Rectenna arrays in consideration of the current voltage balance like this. When we keep the same voltage, in there is no decrease of the output power, or we put the Rectenna element with a different power areas in this near field, radiative near field rectifier, for example. So in consideration of this rectifier connection, it's better to consider the connection to keep the high output power for the high microwave power rectennas. So, and last, maybe I don't have enough time, so this is just information for you. So when we don't have enough, we don't have a good gallium nitride or good circuit technology, but the user requests 1 kilowatt, for example, for the microwave receiver. So in this case, we have a microwave tube technology, vacuum tubes. Of course, some of you consider, so I sometimes use this. The end of microwave tube is invisible, so your kind is heading to extension. Maybe some of you know this very famous word. So Tom Cruise replies, maybe so, but not today. So I show you the new microwave tube technology instead of the device. So for example, this is of course originally old technology. William Brown proposed a very interesting multi-factor rectifier. He said, I found this only one paper, and this is only one concept to rectify the hyper microwave by the vacuum tube technology. But there is no real picture of developed this multi-factor rectifier by William Brown. So this is only a concept of the high power microwave tube by William Brown. But in Russia, they really developed a high power rectifier named cyclotron wave converter. This is a real picture. And this is combined as a microwave electron beam, electron beam and conversion area of the magnetic field. So originally, this is originally from the crystalline of the TWT, and when we are the microwave around here, and after the propagation of the electrons here, and microwave power added to this electron beam, and by the cyclotron motion, this electron moved to the rotation in this area. But around here, suddenly magnetic field inversed the other side. And as a result of the same cyclotron motion, and this cyclotron motion suddenly stops, and finally all electrons attack to the only one side of the area, because it means around here only the minus, negative voltage occurs, and from here they add the microwave power into the electrons, and as a result they gather the direct current from this area. This is a theory of the cyclotron wave converter, and they developed it in the real in 80s. And so this is a computer simulation of the simulation of the electrons, motion of the electrons. And theoretically, this is our result with help of the Russian group. And theoretically, conversion efficiency of the rectifier CWC reached over 96%. And in their paper in Russia, they have already reached over 90% at a kilowatt or 10 kilowatt at the S band or the other. But unfortunately, so this was real. But recently, there was no paper to describe the cyclotron wave converter from Russia. So I hope the group keep this research of the cyclotron wave converter for the high power rectification in future. So that's all my talk. I spent 2 hours. So this is a conclusion. So this technology or the rectification is described in this new WPT book. And I bring this book around here as a sample. So if you are interested in this book only today, I bring it as a sample here. So please read it and please learn a lot of WPT technology from these books. And this is my real last figure. I always use it. So this is our dream, Wireless Power Society. So when we are in the room, we can charge our mobile phone automatically. When we can charge our vehicle, for example, or we can transmit a very huge power from the space. This is based on the wireless power technology. So this is our dream, but this is the last word for young students. So best way to predict the future is to invent it. So this is my dream, but please don't ask me the future. So please invent it by yourself. So it's the easiest way to predict the future. So that's all my talk. So thank you so much. So do you have any questions? So do you have any questions or comments? Yes, please.
A very quick question. You gave us an excellent overview of what developments in the circuit area.
Got very good guidance on the Rectenna antenna, the circuitry, the diodes, etc. I'd like to, and you also pointed out that we can get 100% efficiency. But if I'm correct, if I understood you correctly, this 100% efficiency is over the stretch which begins from what power the antenna flange gives you and all the way to the end where the power is used. So I agree, it's a good news that you have 100% efficiency, but at the antenna end, you have a physical area, and so my question is, what is the highest efficiency of an antenna in terms of collecting area? So if you have a physical geometrical area of, I don't know, 20 centimeters squared, so what is the state of the art that 20 centimeters squared of space in which the antenna is placed, that a pointing vector of electromagnetic wave reaching is what's the maximum absorption which can take place? Because I would have imagined this is the fundamental roadblock as well, in addition to the wonderful things you told us.
Thank you so much. Thank you so much. So of course, I explained a lot of ideal theory, but in the experiment, it's a very old matter by William Brown. But in this experiment, here you can see the whole antenna, and this is a rectangle. Experiment he reported So for 54% from DC to DC via microwave. And we can analyze in each efficiency. And at the transmitter, of course, it's a very old matter, and he applies a magnetron microwave tube, and efficiency reached about 80%. At the beam efficiency, from the antenna to the it involves receiving efficiency and the beam efficiency, or antenna to antenna based on my analysis. Approximately over 90% efficiency was already achieved. And at the receiver, he was a pioneer of the Rectenna, and 82% at the Rectenna array. So, and as a result, multiply 80%, about 90%, and 82%. In his paper, he reached 54%. And in this meaning, mainly antenna efficiency. It involves beam efficiency and antenna receiving efficiency, of course, transmitting antenna efficiency. All involved, he achieved approximately 90%, for example. And theoretically, when we expand the distance, and based on the Friis transmission formula, it's easy to realize a large antenna, and we keep the same frequency. So, Professor Naoki mentioned solar satellite, and we based on his experiment, we will launch the over 2.2 kilometer size of the antenna. And at the ground, we put a 2.4 kilometer size of the antenna. And based on his technology, we can realize totally 50% from the DC to DC, even in the 36 kilometer above, 36 kilometers distance. So I showed you today mainly the theory, and additionally a small experiment. But William Brown has already reached over 90% beam efficiency multiply antenna receiving efficiency. Thank you so much. Do you have any? Yes, yes, you have. Yeah, no, please.
Again, I think it's a question that goes to both speakers, to you and to Professor Calvarot. We talked about power transmission from A to B, say from satellite to the ground. And you talked about the frequency, the allocation, which frequencies might serve best. In all these considerations, did you also consider the influence of propagation through the atmosphere?
Yeah.
There will be attenuation through rain, through clouds, and here the frequency can shift the optimal frequency. For circuit theory, you may have one optimal frequency, but in terms of attenuation through the atmosphere, there may be another optimal frequency. So how would you comment?
Yeah, thank you so much. So in Japan, we have already estimated the attenuation of the rain or the clouds or the air itself. And based on our analysis, of course, it's originally from the analysis of the attenuation by the radio communication, satellite communication was the other. And as a result, attenuation by rain or the air itself was the other. Very small, maybe up to a few percent only, even in normal rain. Normal rain occurs in the day by day, for example. So we choose 5.7 gigahertz now. So it involves three meaning. One is a frequency allocation as a commercial business of the wireless power transfer now. It's in the ISM frequency. So we chose a 5.7 gigahertz. And we would like to reduce the size of the antenna. So now we choose the same frequency, but of course, only we consider the size of the antenna. Higher frequency is better. So 35 gigahertz, 65 gigahertz is better to reduce the size of the antenna. But maybe you know, radio window by the wireless satellite communication. So up to 10 gigahertz, attenuation by air of the rain is very, very small. So we choose a 5.7 gigahertz only to realize a solar power satellite. Of course, some of you consider, now I explain, 2-kilometer size of the antenna in the space is very huge. I really understand it. But if we increase the frequency, as now you indicated, rain attenuation or the air attenuation, so unfortunately we cannot increase the frequency for the solar power satellite. And of course, it involves the effect of the plasma physics. And in the ionosphere, there are some nonlinear interference between the hypermicrowave and the ionospheric plasma. So in this URSI, we have some international commission activity for the solar power satellite with the commission GHF or the other. Maybe you know, they are always considering about the atmospheric science or the plasma physics or the other. And my boss was a plasma scientist. And we estimated some nonlinear interference in the ionosphere by the hypermicrowave. For example, three-wave coupling effect or the microwave heating or the other. And all we consider, fortunately or unfortunately, we choose a 5.7 gigahertz now.
So is the magic frequency of 5.2 gigahertz, is it a ideal choice based on physics and modeling, or is it a choice based on practical approach?
Yeah, this is a practical approach, and now maybe you know, now in the ITUR, for example, International Telecommunication Union, we are discussing about the suitable frequency for the wireless power transfer. ITUR recommend 920 megahertz and for 5.7 gigahertz, and additionally 61 gigahertz suitable for the wireless power transfer business. And based on this business matter and frequency allocation and attenuation by the air or the X-ray or the effect of the ionospheric plasma, or we consider and we choose a 5.7 gigahertz now.
I can share by my own experience. At 5.2 gigahertz, you can easily have an attenuation of 6 dB through the ray cloud, and which means you are losing more than 50% easily.
Yeah, I agree. So if rain is very, very, so there is heavy rain, so you're right, I think. So it depends on the amount of the rain. So we choose 5.7 gigahertz because compared to the 2.45 gigahertz size of the antenna, we can reduce it. Thank you so much. Thank you for your comment.
Thank you very much.
So maybe it's time to close. So thank you so much. About 20 minutes break.
Yeah, I was just trying to get the program. Just one moment. Yeah, we will come back at 4 p.m. for Valentina Palazzi talk. So thank you very much. Have a nice